big things about this unit is being able to tell whether an acid is or the substance you have is a proton donor or acceptor. So we're really not going to use Arrhenius's ideas about acids and bases because they are so limiting. And we'll look at today actually a quantitative way to figure out if something is strong or weak using the equilibrium constant. So Ka, A for acid, and Kb, B for base. Okay? And hopefully you can already write conjugate acid-base pairs. If you didn't do any of the first day homework, then when you go to, especially tomorrow, when you go to write your own ice tables, you have to write a dissociation equation first. So if you don't know how to do that, maybe go back and start there. We are going to use the Kw relationship, pH plus pOH equals 14. Percent after today, percent ionization. So I could give you really very little information, and the question could be out of sometimes I make a huge question out of 12 marks because there's so much you can do with very little information in this type of problem. Because as we've talked about, due to the ionization of water, then there is always, especially if the substance is weak, then there's always protonation of water, so you can calculate H concentration, OH concentration, pH, pOH, etc. So the stronger the acid or the base, then the weaker its conjugate. So in fact, these substances have no reversibility. So their arrow is not equilibrium, which means no ice. So the problems, the mathematical problems you have done before, you should not have done an ice table. Whereas today, when we look at how strong an acid or base is based on the proportion, the number or the amount of hydrogen ions produced per mole of acid or produced per mole of base, then that is going to determine whether something is weak or strong. Oh, and it says that on the next slide. Okay, so when you have HCl, which is a strong acid, that means there is 100% ions in the solution. Technically, HCl doesn't exist. So the lack of an equilibrium arrow for the reaction means no reversibility. So there was one question, I think from the first day in the homework, and it says, what's the concentration? I think it was nitric acid, HNO3, and the answer is 0 because HNO3 together doesn't exist when you have something dissolved in water. Acids are water loving. Strong acids, the reaction is 100% complete. Again, there is no equilibrium arrow. The ions on the product side do not act as donors and acceptors. So in the past, when we first, like in grade 11, when we first teach you about trying to write down acids and bases, label them proton donors, proton acceptors, we often choose HCl as the acid, or something like sodium hydroxide as the base, to try to give you a chance to try to, okay, I know that's an acid, to see if the proton transfer, figuring it out, works. But really, we shouldn't do that, because the hydrochloric or the chloride ion here actually does not act as a base. It is a very, 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 very weak conjugate. Later on, when we do titration, we're going to say that it is not a legitimate conjugate base, like it does not accept a proton. So there is no reversibility. Whereas weak acids, about 1% of them dissociate. So again, we're trying to get away from about 1%. Well, let's calculate exactly how much. And again, this is ethanoic acid, or vinegar, commonly known as vinegar. So they're writing it in this notation is trying to emphasize that this is the hydrogen that's lost. So a lot of the questions, a lot of the weak acids you're going to get are ethanoic, methanoic, organic acids. Even when we do buffers as well. So these are a very common choice for a question. So there is mostly acetic acid or ethanoic acid molecules, and there's only some ions. So there is an equilibrium arrow, which means that there is considerable reversibility, and the ions on the product side are going to be a legitimate conjugate base and acid. Okay, so in this example, so this is negative, it's going to be a good base or a good acceptor. Actually, let's write that better. Hold on. And so when you have a reaction that is reversible, that can go back and forth, then that makes it so it's subject to Le Chatelier's principle, which is predictable and easy to prove. And when you can have a conjugate base like CH3COO negative accepting protons readily, and then you would call CH3COOH something that will donate protons readily or be an acid, then now you have both kinds, an acid and a base, in a solution, which then is going to make this type of solution maybe possibly a good buffer. So we'll do the fundamentals today, and then we'll look at how we can, and tomorrow, and we'll look at how we can then affect the shift or stress the equilibrium on Wednesday. Okay, so if you have the note printed off, the next two slides look almost identical. So the ideas of the equilibrium constant are the same as last time, products over reactants. You only include aqueous and gases as well, but in this case, it's going to be all aqueous. And we can use the size of the K value to determine the direction of the reaction, just like we did in the first section. So Ka, A stands for acid, then it is calculated. So any acid we could technically write this equilibrium expression. The products are always ions in a dissociation equation. So it's the concentration of the ions over the concentration of the acid. If you look on page 803, there is a list. So there's a list. It says Ka for and Kb for common acids and weak bases. So all of the acids at the top: perchloric, hydroiodic, hydrobromic, hydrochloric, nitric. Those are very, very common strong acids, and they don't even give a Ka value. It says very large. So the reaction is so far to the right, 100% complete. That means that the top of the fraction would be very, very big, making the K value super large. So then you can't, in a mathematical equation, like an ICE table, you can't use the letters very large for anything. So when you are given an actual Ka value or Kb, like this question, Ka is 1.8 times 10 to the negative 5, then that can be a clue that you have a weak acid or base. So you can use it to tell you whether something is weak or strong. So the smaller the value of Ka, the weaker the acid, because a small K value means the equilibrium lies more to the left or the reverse direction. So if you have Ka greater than 1, so again, the textbook does not even list a value. It just says very large. And then it's not really a requirement in grade 12 where you have to say if something is weak or moderate. If you're given a K value, then you can just assume that you have to do ICE. So when say it's the test or the exam, I'll give you the number in the question. But when you do the homework, you might have to go look it up. Just like always, your textbook loves to make you go look in the back for the reference values. And when you go to look at the chart, there is a whole, like a huge list of acids and then very few bases. So bases are not as well studied because they don't react like acids do, right? So we've talked about that. There's no bubbling with metals. There's no production of carbon dioxide. And also weak bases are very, 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 very smelly. So practically, then we couldn't do a lab, for example, with a weak base in here because you would have to have ventilation, better ventilation, respirator masks, because the smell is really, really pungent. So the list is smaller for bases because practically you will see less bases in your studies or your work, unless you work in a place where you have some serious industrial manufacturing going on, and then you would have to wear like a suit and a respirator, so not a regular job, so to speak. Okay, so then, like I said, this page looks almost identical. Now, strong bases are a little bit easier to pick out because their chemical formula will always have OH in it, but we can also do it this way as well. So when you have a base, then it's, again, the ions, so the conjugate acid, BH plus, and OH concentration over the concentration of the base. The smaller the value of Kb, the weaker the base, because there is a little bit more reversibility, meaning the base concentration or the bottom of the fraction is not very small. It's a little bit bigger. But again, they are a little bit easier to pick out qualitatively as well, like you would have done in grade 11. Okay, so the first calculation we're going to do is percent ionization. So again, so far in the note, and even in grade 11, it said about 1%. We don't want to do that anymore. We want to be exact. So you can calculate percent ionization, and just like always, it should be less than 100, and in our case here, way less than 100. So that means the ion concentration, which is in the top of the fraction, should be less than the original acid or base. Most people will associate an acid with hydrogen, so that's why I put the hydrogen ion concentration on the top. You can use either ion. Okay, so percentage, calculating the percent yield or whatever of a reaction, if you remember from grade 11, that was one of the easier calculations. So when you get down to doing this, then you've done a lot more work beforehand. So in our first example today, all we're going to do, we're already given pH, so we can use that to do the percent ionization. When we get to tomorrow's lesson, which has a little bit more work, we have to do ice as well, then being given the percent ionization is very helpful, because it's going to help us find values at equilibrium. So just like we did with solubility, it was sort of like you had the solid initially, and then you dissociated it into ions, and that solubility went at equilibrium. The same thing here. We have an acid or a base dissociated into ions, and the amount, or in this case percentage, that it has dissociated will tell us the equilibrium values. So we don't need that for our first example today, but we will need it tomorrow, so let's write it down. Okay, so this example, we just are asked to calculate percent ionization. We're given the pH, we're given the initial acid concentration. So this question is very straightforward. We do not have to do a lot of work. So I'm not going to trick you and ask you to calculate percent ionization for a strong acid. That's not a thing. So if you're asked to do percent ionization, then you can just assume the substance is weak. But again, hopefully by the end of tomorrow, you'll be able to pick that off on your own. Okay, so we have CH3COOH. Like I said, it is definitely a weak acid, and it's I would say 97% of the questions, that's the weak acid that you're going to be given. So you'll just sort of get used to it, okay? But you could look it up. Okay, it is a small Ka value. Every single organic acid is a weak acid, so if you see the COOH, that means it's weak. Another piece of information here we're given is the pH. So last week when we last whatever time we were here, when we calculated pH for, I think it was nitric acid, our answer was negative 0.6 or negative 0.4, a very, 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 very low pH. 2.96 is definitely below 7. It's definitely on the acidic side of things. However, it is not very acidic. So when you have a pH that's low but not super low, that's another way you could tell that it's a weak acid. Or like I said, I'm not out to trick you. If you're asked to calculate percent ionization or you're given percent ionization, the substance is weak. So when you write the formula, it's on the formula sheet in general terms like H plus over HA, which is the concentration of acid. You can leave it like that. You can write it with this acid and its conjugate or the H plus if you want to. It really doesn't matter. Okay, so you have to fill in, if we're looking for percent ionization, that's what the question says. That means that we need to be able to find the H plus concentration, the acid concentration, and then of course percentage is always times 100. So the question says 0.1 molar acid solution. Percentage has no units except percent, so it's up to you if you want to write in the M or not. That doesn't matter. And then we have to use the pH to find the H+. So again, another formula, that's on that formula sheet is the inverse of log 1. And in fact, after tomorrow's lesson, you'll see every time we have pH, you're going to do this. So you could just even do that first, whether it's an ice table or not, get some part marks. Use scientific notation or not, I don't care. Okay, so take a minute and pause. Is this number significantly less than 100? It sure is, okay? So this homework is not very intense. Tomorrow's will be much more intense. So use your class time wisely or your home time wisely, but we have quite a bit of time right now. So that is